Let's start. Yes, welcome everyone to our weekly seminar. So my name is Evgenii, and today I'm gonna talk about Kleene Algebras, its theory and applications. So first, like a bit disclaimer. So I'm interested in this theme of Kleene Algebras for quite some time, but still I wouldn't call myself like an expert in this theme. So if you notice some typos or mistakes during the talk, just raise your hand and we'll discuss this. Yes, so let's start. Yeah, and if you want to just ask some questions during the talk, also just raise your hand or just speak and we'll talk about your questions. Yeah, so first of all, a quick overview of this talk. So we're gonna start with something I think is familiar to most people here, regular expressions. And from that, we'll get to Kleene algebras. We'll consider some interesting non-standard models of Kleene algebras. By non-standard, I mean models that are not just like regular language models of Kleene algebras. And then we'll have a look at one particular extension of this theory of Kleene algebras with Boolean tests. We'll have a look how it helps to encode semantics of imperative programs. And also rules of Hoare logic of correctness. And from that, we'll also have a look at a few other applications of this theory besides this. And at the end, I'm gonna quickly introduce some other useful extensions of Kleene algebras. Yeah, so let's start. Yeah, as I say, we'll start with regular expressions. So I assume most of you are familiar with this. So regular expressions is like a very simple language. Here it's syntax here. So it consists of the following terms. So the regular expression can be just a letter from some alphabet, sigma. We consider it finite or countable. I don't know, perhaps finite. And then there is sum of regular expressions. This is also called non-deterministic choice. This is a sequential composition of regular expressions, Kleene star or iteration, and finally two special constants. The 0 is for an empty regular expression, and 1 is like it's for a regular expression that denotes the empty language, and the 1 is for epsilon string, like a string that empty string. Yeah. So is everyone familiar with this, right? Okay, let's move on. Yes, so the natural interpretations of regular languages is through the languages, through the string interpretation. So we have some fixed alphabet of letters, and we'll consider strings or finite strings over this alphabet. That's just a sequence of letters of finite length. And we'll give the semantics to the regular expression syntax in terms of the sets of strings. That is, in other words, semantics of the regular expression is just a language set of strings. So as I said, semantics of the constant 0 is an empty language. Semantics of the constant 1 is a language consisting of just an empty string. And semantics of a letter is just a language consisting of this single letter. So next, semantics of choice is it actually just a union of languages. Semantics of sequential composition, it's a bit more interesting. We'll take all the words from the left language, and we concatenate it with all the words from the second language. And as a result, we get all the results of concatenation of every pair of words from both languages. And finally, the Kleene star or iteration, it just takes the sequential composition. So it defines sequential composition as we iteratively apply this compose with sequential composition language with result of iterating it n-1 times. Yeah, and you take the union of all such languages and get the result. So it's I think everybody is familiar, but just in case, for example, this language it will consist of O. So first of all, it will have an empty string, then it will have string of one letter A, then A, then A, and so on, like infinite number of times. Yeah, so this is like pretty standard thing. It's usually taught on like any course on formal languages or automated theory. And from these courses, you can also recall that Taylor expressions.
Excuse me, I have a question.
Yeah.
Does the set of natural numbers include 0?
Yes, I think so. Yes. Yeah, because this is like.
Thank you.
Yeah.
And error in power of 0 is just a regular expression that recognizes only empty string.
Yes.
Okay,
yes.
Thank you.
Okay. Yeah, let's move on. So you can also, I think you also remember that regular expressions correspond to finite state machines. So this is also not rocket science. So we have state machines, which are such things. So state machine consists of a finite set of states, finite alphabet, or in this context, in the context of this talk, we'll call this set of labels, labels of actions that automaton perform. The transition relation, which is a relation from state, it will write it down as follows, like S1, L, S2. It means that there is a transition from state number 1 to state number 2, marked with label L. There is a distinguished initial state, and there is a set of final states or acceptance states. And yeah, there are two major classes of state machines. They can be either non-deterministic or deterministic. And deterministic is such a machine such that if we have a transition from S1 by L to S2 and from S1 by the same label L to S3, then it has to be that S2 equals to S3. So in other words, like from each state and by each label we can have just a single transition. So we don't have any choice. If we fix the initial state and the label, we have to arrive at the fixed final state. Yes, and like usually this automaton is presented slightly different. They present it using so instead of regulations, we can use functions to represent the transition. So for deterministic automaton, we can use a function that just takes state label and returns the resultant state. And for non-deterministic automaton, this function should return a set of states because like we have a choice where we want to go, because from the same state and the same label we can go to different directions. Yeah, and like the classic result is that it basically says that every regular expression can be recognized by some finite state machine, either deterministic or non-deterministic. It doesn't important they have equal power, and vice versa. Like for each deterministic state machine, we can build a regular expression that denotes the language that is accepted by this machine. Yes, by the way, language accepted by the state machine is defined as false. So we take we basically say that word is accepted by the machine if we write it as a series of letters I, B, C, etc. And then there should be a path in this automaton starting with initial state, then going consequently by all the letters of this word, and finally on the last step it should arrive at one of the final states. Then we say that this word is accepted by this automaton. Yeah, so yeah, I guess you all knew that. In case you don't have, then just ask questions.
Does the definition of automaton is equivalent to the definition that allows for epsilon transitions? In other words, transitions that are performed by an empty string.
Yeah, so we could do both. Like we could define automatons that don't have epsilon transitions, or automatons that can have epsilon transitions. Yeah, so this definition that I give here, yeah, it assumes that there is no epsilon transitions. If we allow epsilon transition, then like we can insert them in any on any place in this path. We can insert arbitrary number of epsilon transitions. So yeah, it's just a bit clumsier definition. Yeah, but again, they are like have equal expressive power. We have a procedure that can eliminate our epsilon transitions in an automaton. Okay, yeah, let's move on. So yeah, this theorem is known as Kleene theorem, and it has it's one of the cornerstones of the computer science theory. So yes, I will not dive deep into the proof of this theorem. However, I want to touch one part of this proof because it kind of demonstrates the point that I want to demonstrate. So in one direction, in this direction, the proof goes as far. There is actually several proofs. I'll touch one of them that uses non-deterministic automatons, and so this proof goes as follows. It goes as follows. So we assign to the syntax of regular expressions slightly different semantics. So this semantics, instead of mapping regular expression, like term and regular expression language into a set of strings, instead it maps regular expressions to non-deterministic automatons. And this is this can be done pretty easy. There's nothing complicated here. Yes. So for example, if we can map a constant 0 to automaton that just doesn't have any final state, so it's never going to accept anything. This automaton, this is just an automaton that immediately arrives to its initial state is also its final state, so it accepts an empty string. And next, like you can guess what happens. This is an automaton that accepts one letter. This is an automaton that at the beginning it makes a choice, like it either goes to the first automaton or it goes to the second automaton. And this automaton, it starts working same as the first automaton, and then by epsilon transition it continues as a second automaton. And for iteration, it's basically a loop in automaton states. So what I want to demonstrate that is that we had a syntax of regular expressions, and we assigned first to it denotational semantics in terms of set of strings. But now we also invented another semantics for the same language, and that interprets this regular expressions in terms of automatons. And from that, we can ask a question: can we have other interesting models of regular expressions? Like if we manage to do this, perhaps there are some also interesting models, another interesting semantics for regular expressions. And if so, can we have a common algebraic theory that will describe all these models and what we can prove about expressions in these models? So it turned out that the answer is yes, there is such theory, and that's what's called a Kleene algebra theory. So Kleene algebra is an algebraic structure which comes with a bunch of axioms. And the point is that so these axioms, they allow us to reason to prove equivalence of regular expressions or subsumption, or that one expression is embedded or is less than another. So in terms of languages, it means that its language is included in the another. And so this is an equational theory that allows to derive these facts about regular expressions, proof that regular expressions are equal, like they denote equal languages or other objects if we have another semantics, or that they are included. Yes. So what it gives us axiomatic semantics for regular languages, and not only them, but for any model of this structure for this theory. So let's have a look at the axioms. First of all, as you can see, this Kleene algebra signature of the theory is just all the operations that we had in regular expression syntax. And we also can derive a partial order here, and it's defined as follows: like A is less than B if A plus B equals B. Yes, so the axioms.
What does equals mean?
Yeah, sorry?
What does equality mean? In which respect they're equal?
They are equal as modulo all these axioms. Okay, you can have a look at this in two different ways. Yes. So first, if you have some model of Kleene algebras there, so some particular instance of set A, and for example, if we look at strings, how do you know this? So set of regular languages, before the when we interpret all these operations as operations on regular languages. Then we can when we can talk about equality as the quality of languages in terms that the two languages are the same sets of strings, right? So this is like equality.
So two regular expressions are considered equal if they recognize the same language.
No. Wait a bit. So this is one type of equality we can talk about. Yes, this is like an equality in our model. Yes, like underlying equality of objects in our model, right? Another equality that we can talk about here is syntactic equality. I think that is how it's called. It's like equality if we'll all what we can prove equal using these axioms. So if we, for example, can derive that, I know we can derive, I know yeah, so we can, using these axioms, we can derive this, that this expression is equal to just a plus b, yeah. So this is another equality. So these two types of equalities, they don't have too much, it's different. They're different, right? So we could have like a model where we have objects that are equal, but we can't prove this using these axioms.
So basically, in the second case, we define an equivalence relation that is given by those axioms.
Yeah, if you want to be like completely formal, you need to consider all the trees consistent of this, all the trees in this signature. Then you need to consider like equality as the least congruent relation derived from these axioms. It's like an inequality in the free model of this signature.
So there is the concept of a free group involved, yeah?
Free what?
Free group.
Not the group, but like free Kleene algebra. Like for any algebraic structure, you can have what is called like a free model or free structure. It's a structure that only had like I don't know how it is also called like initial algebra, I think, in computer theory. But the point is that this is the structure that has in free algebraic structure, its structure is basically just the structure of the theory itself. It has nothing, no more structure than the theory itself gives. Like we, for example, we can't have any more equalities than we can prove in the syntactic theory using these axioms. Yes.
So the equality, so two regular expressions are equal if and only if we can derive this equality from those axioms.
Yeah. So this is what we will call the equality, like in terms of Kleene algebra theory. Yeah.
But the other way around is that we can have another underlying model and just prove those axioms. Yeah.
We'll have a look at a little bit later to this. We'll have a way to like reconcile the two. So yeah, for now, let's just like have a quick look at these axioms. So this basically are axioms of idempotent semirings. It says that addition is associative, commutative, A0 is neutral element. It is also idempotent. Then we have like monoid axioms for sequential composition, and 0 is like absorbing element. Then we have distributivity. Yes, and these axioms, they talk about the Kleene star, the fixed point, and yes, so yeah, you can just have a look at them. I can't give any more intuition behind what is written here. So please note that these axioms are actually like unlike all other axioms, which are just purely equational. Yeah, this is actually an axiom. This is actually like a proof rule, right? So it means that it has a precondition, like, or how do you call this formally? I forgot. But basically, it means that. Sorry.
It has premise.
Yeah, it has premise. Yeah, sorry, this type. Yeah, it has a premise. And there was like an existing theoretical result that says that we cannot have an axiomatization of the Kleene algebra theory without these axioms with premises. So we can't have a purely equational axiomatization of this theory. Okay, now, as I promised, let's have a look at some less common models of Algebra expressions that you, I suppose, never heard, but yeah. So one important model is the model of binary relations. So we'll interpret expressions in Kleene algebra signature as binary relations. That is, binary relation is just a set of pairs from some fixed set of elements. And the interpretation is as follows. So again, constant 0 is just an empty set. Constant 1 is identity relation. This is like a relation such that every element is related to itself. Yeah. So it is a relation that consists of all such loops for every element of X. Next, the plus is just a set theoretic union again. So if we have either this or if we have either of this, then we have an edge in the resulting relation. Sequential composition is it's composition of relations. So this is like a join operation in SQL, something similar. So you have, like, if you had an arrow from X to Y in relation in relation N1, and then you have edge from Y to Z, then you have an edge in the resulting relation. Yeah, can you see this? Is it clear? Okay. Yeah. And this is again just a Kleene iteration. We can again define it the same way as for languages, just as a union of all powers of the expression. Yeah, semantics of the expression. And again, we have this equation. We just use different interpretation of the sequential composition. Yeah, so in terms of binary relations, I will sometime write sequential composition as follows using semicolon. Okay, so yeah, and yeah, now another important note is that this actually gives us reflexive transitive closure of the relation, right? So if we had x, x1, x2, etc., xn in the original relation, then it will have an edge in the resulting relation, and for every such chain. Okay. Yes, and so now what is okay? Let's skip this for now. Let's talk why do we need that? Like, what's the point here?
Okay, can I have a question?
Yeah.
What is the intuitive, I don't know, explanation of this model? Why do we choose regular expressions to be binary relations?
I mean, there's it just happens that like it's interesting model because it has applications, some interesting applications of this model. Yeah, it's basically just that we don't choose it. We just notice that like binary relations can form this algebraic structure, and then like as always in algebra, if we prove that some model like satisfies the axioms of some algebraic theory, we can use this algebraic theory to prove facts about these objects. Like, you know, same as
okay, so
mhm.
This model satisfies all the axioms of Kleene algebra.
Yeah, sure. It satisfies all these axioms. Yes, and another like why it is important, why it is interesting, because binary relations, they quite often occur in computer science, and for example, later we'll see like one way when we encounter them is we can interpret computer programs, for example, imperative programs, as a relations. Like any imperative program can be seen as a relation that takes like initial state and maps it to final state, right? And yeah, so this is like an interpretation of computer programs as a set of pairs, yeah, of initial and final states. Or the same way, I don't know, if you have like a function in function program, you can see it as a relation that maps like argument to output. So yeah, and what it gives us, it we'll like touch this later, but it allows us to reason about computer semantics of computer programs in terms of Kleene algebras.
Does this have any connection to our logic?
Yeah, we will see that too.
Okay,
yes. So the point. Okay, let's just get to the interesting part, because I don't know, we can't. Yeah, so important part first. Okay, so first of all, why should we care? Yeah, why do we need this at all? Yes. So the point here is that if we show that our set together with operations on it satisfy the axioms of Kleene algebra, then we can use Kleene algebra theory to prove equalities of objects in this model. Yeah. So yeah, to have this a little bit more formal, we will define two notions of the equality, as I said. So the first notion is this syntactic equality. So this we'll write it as follows. Yes, so k dash e1 equals e2. It means that this equality of two expressions in Kleene algebra signature can be proven using axioms of Kleene algebra. Yeah. Another equality, it's equality in the model. Yeah? It's a little bit trickier. So we first fix some family of models. So for example, we can fix a family of all the language models. So for each alphabet, like each alphabet induces a model, yeah, of languages over this alphabet, and same for each relation, for each set induces a family of models of binary relations over this set. Yes, so that what we'll call a family of models. And then we'll say that like this model equality in our model, we'll say that two expressions are equal in the family of models if their semantics under arbitrary interpretation is equal. So what is the interpretation? So you call that in the regular expressions or Kleene algebras syntax, we can have also these letters, yeah, and we'll treat them as as variables, yeah. And in order to map the expression in Kleene algebra to an object in our model, we need to give a evaluation for all the variables, right? So, and here we mean that two expressions are equal if they are equal under every possible interpretation. So, is everything clear here?
What are expressions again? What is the language? What is the language of expressions?
A language of expressions is just it's all expressions that can be built from this signature, and also we can use this variables. We can write this. This is an expression in Kleene algebra. This is an expression in Kleene algebra, and etc. So we can use all the separations, and we can use variables.
What is A again? Capital A in the signature.
This is a carrier set, like okay, yeah.
Yeah, I get it. So elements from A. So our expressions are elements of A. Am I right?
No, expressions are just trees, abstract syntax trees in this signature. It's actually a bit misleading. Like this carrier set, it's more like how we define a monoid, right? We say that monoid is a set M together with operation plus and zero element, right? And then we, for example, can say that I know matrices form a monoid or something like this. Like we'll fix this set for each particular interpretation. But here we talk about expressions in this Kleene algebra signature. So these variables, they are not from this set. It's not that they are from this set. Yeah, it's just it's just variables. It's like placeholders for the things that we will talk about. I know. Yeah, so here we need to first map all these variables to actual objects in our model, and this is what is called an interpretation.
So X is A from Kleene Algebra definition.
Yeah. That's like a fixed set, our model of Kleene algebra theory. Like for example, a set of
So evaluation is a mapping from variables to elements of the model carrier.
Yeah, exactly. Yes, and so the soundness and completeness theorem for Kleene algebra says us that exactly what we would expect. Yeah, so this syntactic equality is equivalent in the equality under our family of models. Yeah, and in particular, it can be proven that for these families of models, for the language models, for the relational models, and for the trace models that we'll talk later, these are all like they are sound and complete. Yeah, like Kleene algebra theory is sound complete with respect to these models. Yeah, and it means that we can like every equality in our models can be proven in our Kleene algebra theory, and vice versa for every equality that we can prove in the Kleene algebra theory, it has to be true in the model. So is that clear?
What is the question again?
The question is that clear?
Okay, it's hard to bear in mind this definition.
Can you understand what happens here?
Can you give me a moment to understand the definition of semantic equality again? Wait a second. So we have evaluation that maps variables to concrete elements from the carrier, but what does evaluation from the expression means? What is this?
We just like traverse the expression and apply it to all the variables.
What does it mean to apply? We don't have an interpreter.
We do have like we have a model, and the model is basically like interpretation of all the operations.
We apply all the operations. So operations are functions, so we apply all of them, and the result of evaluating our evaluation on an expression is just another element from the carrier.
Yeah, so I know, for example, we have expression a plus b. We want to interpret it, I know, under an evaluational model when we have a that denoted like this relation, and b that denote this relation. It's a relation that consists of a single pair. Yeah. So how do we do that? We first, okay, we need to apply like we put the semantic brackets through we push them through the syntax, right? So we took like interpretation of the to us, which is in terms of binary relations, just the union of the relations. And when we have also, we need to interpret these variables, and for them we have an interpretation, right? So this is this relation, B is that relation. So, and then we just take their union and we'll get the relation which is xy and yx. Can you see?
So this definition says that under every evaluation, after applying all of the operations, we should end up with the same elements.
Yes, they should be equal.
Okay, thank you. It's now becoming more clear.
Okay, and now can you decipher this?
So I am expected to understand this intuitively, yeah?
You have all the ingredients now. Yeah.
Well, I believe that. What does lang mean
So
in this statement?
So this here
I
says that,
I see.
yes. So this is like model equivalence under all regular language models. This is like, remember that we defined this with respect to some family of models, right? So this is this is true for all the language models. This is for all the relational models and trace models that we haven't defined yet. But the point here is that this term allows us to like go back and forth, like from model equality in the model to the equality in the theory and back. Yes, so it says that if we can prove equality of some Kleene algebra expressions using axioms of the Kleene algebra, then it should be true that this this expression should be equal under language model, right? For any language model. And vice versa, for any equality of two expressions under language model, it should be, it can be proved using axioms of the Kleene algebra.
So this theorem states that all of the models for regular expressions are equivalent, and moreover, Kleene algebras, axioms of Kleene algebras, cannot encode anything more powerful than languages for regular expressions, than models for regular expressions.
Yeah, something like this. Yeah, it basically says that the Kleene algebra theory doesn't distinguish these three types of model. They are all the same from its point of view. And yes, and you can, like, it also means, yes, that you can decide the equivalence of two expressions under any of these models using the same algorithms that you would use for the standard interpretation, like for the regular expressions. It basically means that you can use these problems to check in the equivalence of two regular expressions.
As far as I remember, this is a very complex task from the point of view of complexity theory.
Yes, it's if I remember correctly, it's p-space, which is bad.
Yeah, it's p-space complete.
Yeah, but nevertheless, it's decidable. It's already a good. Yeah, And so, yeah, the good point that we should note here is, yes, this Kleene algebra theory doesn't distinguish these three models. And this is, as we'll see later, this is not always true for all the extensions of the Kleene algebra. So when we start to add some new operations of the Kleene algebra, usually it happens that these models are not equivalent. We need more axioms for some models, or we need like incomparable set of axioms for various models. So it's another like surprising in some sense result is that like in Kleene algebra all these models are equivalent. Yeah, by the way, let's have a look at this model. So what is this trace?
Another notice from this statement is that Kleene algebra always gives us a free structure.
Yeah,
terms that equality can only be derived. So none of the models can give us more equalities than pure derivation from the axioms.
Yes.
Okay, thank you.
Yes, okay, so let's have a look at this trace model. So trace model, it's a bit similar to relational model, but the difference is that like in relational model, we just record like the initial and final points, right? And here we collect the whole trace, like the whole path in the graph. So yeah, we usually interpret it over like Weber transition systems, which is just the graphs. Actually, they could be infinite. It's not necessarily a finite graph, but it's just a graph where we have states, set of states. We have edges labeled with our labels and so on. So it's just some graph. Okay. Yes, and so oh, sorry. What just happened? Yeah, sorry, I just my iPad left the meeting. What happens? Okay, let me then continue without an iPad.
Can you please share a couple of slides in the chat so we can just scroll in parallel and go back to the definitions without asking you to?
Can I share files in Google? I don't think so.
Yeah.
Okay, then it will take some time. Okay, let me. Because we are running out of time, so it's just like half an hour, and I had like a large number of slides. I thought we'll get quicker there. So let me just finish, and then I'll share the slides, and you can skip them through. Yes, so we finished here right on the trace models. Yeah, can you see the slides? No? Hello?
Yeah, we can see the slides.
Okay, good. Yes, so we had this label transition systems, then we can define what trace in this transition system is. It's just like a sequence of states and labels, such that there is a transition from all the neighboring states by the given label. And then we interpret Kleene algebra expressions as set of traces again. Yes, so what happened here? So again, the zero, the constant zero is just an empty set, the constant one is just an empty trace. We can interpret all the letters, all the labels as just all the traces of the length one that has this label. Then union, like plus, is just a union of set of traces. And what is interesting is what is a sequential composition of traces. So it is defined as we take all the traces from the semantics of the left expression and all the traces of from the semantics of the right expression, and we join them only if their endings match, right? So if the left ends with a state, the same state as the right trace starts with. So is it clear?
So the next pass, pass is the compositional, is sequential composition, is a concatenation of paths from interpretation of R1 and R2.
Yeah, but only if their endings match. Yeah. So actually, this definition is not quite right, because we also need to handle cases when one of the traces is an empty trace, right? So for example, if we had if the semantics of the R2 accepts an empty trace, then we just need to take include all the traces from the left expression and vice versa. Yeah.
In other words, we could just write that the concatenated path has just to be a correct path.
Yeah. Yes. Okay. Yes. So why is this interesting again? So in some for two reasons. So in terms of if we think about this transition systems as graphs, this actually gives us a way to encode paths in the graphs, right? And then we can use it, for example, to perform some path search, like search of all the paths that are accepted by these regular expressions, right? Like we can perform path search of all the paths that are recognizable by some regular expressions. And next, if we review this from the point of view of the programming language semantics, this basically like this web transition systems, they give us operational semantics, and then again we can interpret this as the traces of our programs, like the sequence of states and actions that program takes. And then again we can reason about semantics, the small step semantics, using Kleene algebras. So what is what's lacking here actually is that if we took this view, right? So the view that this is states of the some interpreters, some operational semantics, and so currently our syntax it allows us to talk about only the actions, right? Only the actions that the system can take. We cannot reason about the states, right? So there's no way here to, like, for example, restrict some states, like say something like we need to walk through the state that satisfies some predicate, something like this. It is not expressible in the signature. So here comes the tests, the Kleene algebra with tests. So this is an extension of Kleene algebra that adds to it a capability to use predicates over these states. So if we speak about this trace model, these tests, these are predicates on the set of states, and we can use it to, for example, to, as I said, to filter out some states, some paths that contain some states that do not satisfy predicates. And formally, this is an algebraic structure where we have a Kleene algebra, and we also have another Boolean algebra. This is just a Boolean algebra, like in the usual sense. Here are the axioms of this algebraic structure. So it has or and end, logical or, logical and, true and false constants, and negation. And we also need to have a way to embed this, to connect the two, and we connect them using this embedding function. This is a function that takes a Boolean test, like an element of Boolean algebra, and maps it to the element of the Kleene algebra. It should satisfy the axioms shown on the right. So, for example, the result of mapping logical or should map to the plus in Kleene algebra, and mapping intersection or logical and should result in sequential composition in Kleene algebra. And next, the false should be mapped to 0, and the true should be mapped to 1. Now, so yeah.
I have a question.
Yep.
Is this specification complete for the usual understanding of what a Boolean algebra is? I mean, that can I imagine that all of the operations are defined as usual?
What do you mean by that?
I mean that AND is kind of conjunction is a logical AND, and disjunction is a logical OR.
Yes, in the sense that they satisfy all these axioms. Yeah, so basically, like, yeah, like Boolean algebra is it's just axiomatization of what you would expect from a Boolean algebra, like from logical or and end and true and false constants and so on. Okay, so yes, and now what is the interpretation, like in all the models that we spoke about? Let's talk about what's the interpretation of these tests. So first of all, it's let's talk about binary relations model first. So here, these tests are, they will be interpreted as subsets of identity relation. Like we'll have, like for test A, its semantics would be a set, okay, its semantics will be a set of all elements of X which satisfy the predicate. And then when we map it to the relations, it will be an identity, a subset of identity relation that maps only the states that are that satisfy this predicate. So here in the trace model, it's as I said, it's it encodes Boolean predicates over states again. Yeah, so tests are predicates over states. And now what we can talk about, so there was a question at the beginning, is it related to the Hoare logic? And the answer is yes, and we'll see how they're related. But first, let's have a look at the imperative programming. So like in typical imperative programming language, we usually have some set of primitives, which should include at least the primitives that are shown here on the top. So here goes the first. The skip and abort are just two special commands that say, skip is just a command that does nothing. Abort is a command that terminates the program. Then we have a sequential composition of two programs or two processes. Then we have a conditional expression, which tests some Boolean expression, and then either goes to then or else branch. And we also have while loops. And like depending on the programming language, we can have more. Like we can have another commands. Like for example, we can have commands to assign values to variables or something like this. But this is like what depends on what particular language. The point here is that
yep, skip and abort are commands to control the control flow inside the while loop. Okay.
No, they are just commands to manage command for like in the whole program. Like skip basically just does nothing. It's just like it's not very useful. It's like no open instruction. I don't know, something like this. It does nothing. And abort is just
skip is not like continue in imperative languages.
No. It's not a continue nor break. It's skip just does nothing, and abort it terminates the whole program, not just the loop it is inside in. It just aborts the whole program. Yeah, and like the standard way to assign the semantics to these imperative programs is using so-called big step semantics, and it's as I already mentioned this. We map the syntax to the semantics is just a binary relation that maps initial state of the machine with the final state of the machine. Right, and then we can interpret all these usual control flow constructs of imperative language in terms of Kleene algebras with tests. So skip is easy. This is just constant 1. Abort is constant 0. Sequential composition is sequential composition. No surprise here. Then conditional interpreted as follows. So thanks to the tests, we can interpret it as false. We can take a non-deterministic choice between two expressions. The first expression starts with the test B, the test of the guard of this if expression. and then if it's true, it proceeds as the procedure P1, as a process P1. Or otherwise, it tests for negation of B and then proceeds as P2. So is it clear? Like, is everybody understand how it works?
So basically, we define semantics of our programming language as expressions in Kleene algebras.
Yeah.
And then we can use any model we discussed above.
Yeah, we can basically use
semantics.
any model. Yeah, we actually can use here any model. And this model of binary relations is just like a standard, very common model. It's like used in every programming language course, or yeah, pretty standard thing. And yeah, so for the while, this goes as follows. So we have a Kleene star of test B followed by the body of the loop, and then it should end with test for the negation of the B. So it means that when we leave the loop, the negation of B should be true. Yeah, so this allows us to interpret all the common control flow constructs of our imperative languages using Kleene algebras. Now, of course, if we have some special instructions, for example, for the mutable state, like instructions to assign values to variables, that would not be directly interpreted in terms of Kleene algebras, right? Because Kleene algebras doesn't speak anything about mutable state, or I know what else. What else we can, I don't know, some probabilities or something like this. Yeah, it just takes about the control flow. We can encode the control flow in terms of Kleene algebra. And now why it can be useful, because now we can use this theory of Kleene algebra, or equational theory of Kleene algebra, to prove equalities of programs. Yes, so again, it does mean that we can prove anything about our programs if it involves some domain specific computations, for example, with mutable states that's beyond the reach for the Kleene algebra. However, we can prove equalities if they only involve around control flow, right? So for example, we can prove, we can denest the while loops if we have something like nested loops, while loops that test for the same Boolean variable, then it basically can be like unrolled into a single loop or something like this. Yeah. And the people actually like observed this quite some time ago, and there was like a seminal work by Cousin and Patron in year 2000, and when they use this to like this use this encoding and the Kleene decision procedure for Kleene algebra to prove soundness of various compiler optimizations involving control flow. So there's here the list of some of the optimizations that they managed to prove using theory of Kleene algebra. Again, it's not that they used only the axioms of the Kleene algebra. It's just that they use it like Kleene algebra together with some domain-specific knowledge to, for example, to reason about assignments or something like this. But then when it comes just to prove equality model of this control constructs, it can be used. It can be done automatically using the equation theory of Kleene algebra. And next, there was a question about Hoare logic, and it turns out that Hoare logic also can be expressed in terms of Kleene algebras. It's also due to Cozen. The result is due to Cozen, and this is again not something complicated. Yeah, you can guess by itself. So if we will have a look at this Hoare triple shown on the left here, so the Hoare triple says that if we have program P and it has a precondition B, then it should satisfy postcondition C. In other words, if we start from any state satisfying B, execute program P, we need to finish in a state that satisfies C, postcondition C. So if we rewrite this a bit in terms of the binary relations again, yes, so we can first formulate it as follows. We took the codomain of the relation, which starts from test B and then proceeds with P. Then it says that this codomain of this relation should be a subset of C. In other words, all the actual states should be a subset of states allowed by postcondition. Yes, and from this, this can be rewritten in terms of Kleene algebra. And sorry, there's a typo here, another typo. So the formula should be: we start with the test B, then proceed as P, and then test the negation of C. Here should be the negation of C, and this expression should be equal to 0. Yes, and so it basically means that.
There is a question in the chat.
I can see this. Okay, question. What does expression square brackets star composition with? Yes. So again, we remember how we define these tests. Yeah, when we define Kleene algebra with test, we also had this embedding operation. So this embedding operation, it lifts tests to elements of Kleene algebra. So for example, if we talk about binary relations, it lifts predicates over states to a subset of identity relations. And then if we have like a test in square brackets, we can use it as an element of Kleene algebra. We can compose it using all these operations of this Kleene algebra, including sequential compositions. So yes, so here we took this binary, we took this test of B, then we lifted to the Kleene algebra, and then took sequential composition with P, and then sequential composition with test negation of C. Yeah, so in terms of binary relations, this lifting is, as I said, it's like a loop relation that binds only those elements that satisfy the predicate. So it means that we need to start from some state that satisfies B, then we go to like we perform a loop and we go to this state again. Then from this state we go as P dictates us, like we use the binary relation of P, and then we arrive at some state, and we need again we take a loop and in the same state, and this state should be the negation of C should be satisfied in this state. Yes, so we took this expression and we require that it be equal to 0, right? So it means that starting from B we can't arrive to C. Yeah, here is the typo. And it actually, like, the cousin showed that all the axioms of the all the inference rules of the Hoare logic, they can be derived using coercion theory of Kleene algebra. Again, it doesn't. It is true only for inference rules that talk about control flow, like rule for if or rule for while loop. Rule for assignment, for example, it can be encoded in Kleene algebra because Kleene algebra doesn't know anything about assignments or mutable state. And then there is a more recent result. So recently there was this correct.
There is a question in the
Yep.
chat.
When we talk about inclusion, here no, because here we took the codomain. Codomain is and codomain took a relation, and it returns a set of elements, like the codomain of the relation. It's just the set. So C, like the test, if we talk about it as about predicate on states, it's just a set of states, and here we also have a set of states. So it's type checks everything is all right. Yeah, and for incorrectness logic, so incorrectness logic is a novel framework which is like a duo of Hoare correctness logic, and it talks about incorrectness triples. So instead of saying that P should satisfy some post condition, we talk about that if we start from some precondition, execute program P, then we can arrive at some state that satisfies C. Like the set of states characterized by C should be a subset of the actual codomain of the relation, of this relation. So in other words, so if the usual Hoare correctness logic talks about like over approximation of the set of states reachable from program with given precondition, the incorrectness logic talks about under approximation of the set of states that are reachable. And when it comes useful, it comes useful when we want to prove that some bug can occur in the program. We can prove that some error state can be reached by a program. So it's the duo of Hoare correctness logic. And it turns out that this logic cannot be expressed in the regular Kleene algebra. However, it can be expressed in Kleene algebra enhanced with the top element. Yeah, top element not in terms of the Boolean algebra of tests, but in terms of the Kleene algebra itself. So, for example, if we talk about binary relation model, this is a universal relation, a relation that contains all the pairs of elements. And then this is this incorrectness triples can be encoded as the following inequality in Kleene algebra. Okay, we are running out of time actually, so I won't be able to talk about everything that I was planning to talk. So yeah, let me mention some other notable applications of this theory. Another very famous thing is netcat language. So netcat language is a programming language for network protocols. And it's it's the language. It's basically just a Kleene algebra with tests. Yeah, so it has some additional operators that are related to this configuration of network switches and routers and so on. But its counterflow is basically just a Kleene algebra of tests. So what is interesting about it? It's just that it is not just a programming language, but because it is based in Kleene algebra with tests, it comes with a lot of tools, useful tools to reason about the programs in this language. So, for example, we get for free equational theory that can justify optimizations in this language. There's also various tools for modeling execution in this language based on finite automatons and so on. Another recent application that is, I believe it is going to be a topic of the next seminar next week. And it's about applying this theory to automatically derive consistency checkers for checking program executions under weak memory models. So this is useful in development of model checkings for concurrent programs under weak memory. So that there's usually like so usually this model checkers for the concurrent programs, they usually enumerate all the program executions under some memory model. I don't know, can take a memory model of ARM multiprocessors, for example, or Intel multiprocessors, or I don't know, some memory model of the C programming language and so on. And these memory models, they also actually they usually defined in terms of binary relations. And it turns out that we can automatically construct consistency checkers that would check if the given program execution is consistent from the point of view of this the given memory model. This again because it is defined in terms of Kleene algebra with tests, we can basically build some automaton that will check for the whether this execution is accepted or not. Yeah, and another interesting application is to algebraic graph problems. So this algebraic graph problems, this is like a class of problems that generalize path algorithms such as Dijkstra shortest path or Floyd-Warshall shortest path and so on to arbitrary Kleene algebra. And when it becomes useful, it becomes useful because it allows us to generalize various related algorithms in one framework. So, for example, I know we can have a common algorithm that computes, I know, a language accepted by some regular expression, and this is basically can be defined using the same primitives as the algorithm that computes all the shortest paths in the graph and so on. But by substituting the Kleene algebras that is used under the hood, we can get various algorithms. So unfortunately, I have no time to speak about it in more detail, but you can just Google it. It's pretty cool thing. So yes, yeah, we're running out of time, so I'll just mention a few other extensions. So I already mentioned that, for example, for incorrectness logic, we need this top element in the Kleene algebra. And there's also a recent paper that about this theory. There's other useful primitives that we may want to have, for example, transposition of relations. It has the following axioms shown here. There are also Kleene lattices. So this is a Kleene algebras when we add an intersection operation. And another like active area of research is concurrent Kleene algebras. This is a Kleene algebras when we beyond sequential composition of processes, we also have concurrent composition of processes. And yeah, it gets significantly more complicated. And I thought there was some work that gives a free model for this theory, but I'm not actually sure. Yeah, but anyway, it allows to reason about concurrent programs and counterflow concurrent programs. So that's all I think you could. Yeah, I think you learned something new from this seminar. Yeah, so if you have any questions now, it's time to ask.
Okay, I have a questions about the example of encoding imperative language you gave earlier.
Here.
Yeah, this one. What is B?
Here.
Yeah.
In terms of programming language or in terms of its interpretation? Okay, in terms of programming language, this should be like an arbitrary Boolean expression in our language, right? So yeah, so as I said, this is not like on itself, it's not a very useful programming language because it doesn't do anything. It's just like it's just the control for the language. Yes, so we should have like other useful instructions to actually do something, like to assign some to memory or something like this. And then if you have this extended language, then we, for example, can have variables in our language, and then we can here, instead of just true and false, we can put a Boolean variable here, right? And then when we will interpret this, we will say that this test, it should only pass only those states when this variable is true, equals to true.
But you had said later that we can't encode any mutable state. So how can we prove the equality of two, for example, if statements which have different, syntactically different Boolean expressions in the condition?
Yeah, that's true. For that, we need some domain-specific knowledge. Like we can, for example, using some domain-specific knowledge, we can simplify expressions by hand. I mean, for example, we can, if we have two Boolean expressions, we can, simplify them. Yes, using like other rules of our language, domain, like which are specific to Boolean expressions. And then at some point in our proof, we can like use the Kleene algebra theory to like derive the rest of the equality, right? Another thing that I haven't mentioned it here, but yeah, so in usual Kleene algebra theory, we have we can only reason about this equality of expressions, right? So we can only prove that two expressions are equal or not. Yeah. There is an extension of Kleene algebra which is called Kleene algebra, Hohen Kleene algebra, and this is a theory when we can have basically we can have some assumptions, like some premises, and in this theory we have formulas of the form like some equalities of expressions or some inequalities, and then like implication, and then the equality that we want to prove. Yeah, so basically we can consider it Kleene algebra theory when we, in addition, we can have some premises, some assumptions. And if we fix some shape for some particular shapes of these assumptions, this theory is also decidable. And then using this, we can encode our domain-specific knowledge using these assumptions. So, for example, we can encode knowledge that if we assign false to Boolean variable, then in the next state it should be true that the test of this Boolean variable fails, something like this, and we can encode it as like semantics of assignment, sequential composition with the test, with the negation of the test of this variable equals 0, or sorry, vice versa, like assignment of false, then the Boolean test of true, and this expression should be equal to 0, right? We can we can encode it as an hypothesis, as an assumption, and then we can use this assumption to try to prove something in this Kleene algebra with hypothesis. Do you understand something? Okay. Yes, so that's the one way. Another way is that you can perform some steps by hand in your proofs. You can perform some steps by hand, and then when you simplify it enough, at some steps, you can just use Kleene algebra theory to derive some effects, or to discard some sub goals of your proof. Okay, any other questions?
Yeah, and this, as far as I know, Kleene algebras are formalized in the relational algebra library for Coq, so we can use it here.
Yeah, there is a library in Coq. Yeah, this relation algebra Coq library. It formalizes Kleene algebra with tests, and also this extension with hypothesis. It has a decision procedure for them, and it defines a bunch of models like relational model, language model, and so on. Yeah, so you can use this in your Coq proofs. It's like pretty cool library. Yeah. What to say about? One thing about this.
Okay, thank you.
I know it's a bit like one of the drawback limitations of this. So it uses a very strange approach, like non-standard approach to encode a hierarchy of algebraic structures. So this is actually like a common problem in code. Like when you have like a hierarchy of some algebraic structures, then it might become difficult to encode this in Coq. So like a straightforward approach is to use something like type classes, like you do like you would do in Haskell, for example. But type classes in Coq, they are often criticized for various reasons. I myself never used them extensively, but they are criticized for being slow or for being hard to debug. So nobody likes type classes in Coq. And then this relational algebra package, it uses some combination of type classes and canonical structures, but it does it in a very non-conventional way. It's sometimes hard to work with. So I myself, I like the SS Reflect and MathComp libraries, and they have another approach for encoding hierarchy of classes, and these two are incompatible. So if you want to use MathComp and this relational algebra in the same project, it could be a bit difficult. Yeah. So another question is from Mikhail. Are there any works using this formalism for abstract interpretation of programs? I haven't heard about this, but it looks as a good fit. Like, again, you can view abstract interpretation again as this big step semantics, but it doesn't interpret programs in terms of concrete state, but rather as abstract states. And then you can do the same. Like all the rest is the same. Like you also have relations, but they relate abstract states. Yeah, and yeah, then you can use. I think that it is interesting application. I haven't seen any papers on this. Let us know what you get. Okay, so yeah, it's time to finish. Thank you everybody for coming. I hope it was helpful. Yeah, so see you.